video to go over lesson 3.9 on related rates. So this is the first time we're going to be solving sort of real world problems with derivatives. The first question we're going to do is the classic related rates ladder question. If you Google related rates, this question always comes up. So we have a ladder and it's leaning against a wall. So the diagram here is very simple, but this red line here represents the ladder. It's 10 feet tall and it's sliding down the wall. So it's falling towards the ground. And we're given some information. We're given that the ladder is sliding away from the wall at a rate of 1 feet per second. And we are also told that the point that we're interested in is when the bottom of the ladder is 6 feet from the wall. I have a little applet here to show you so that you can visualize this a little bit better. Sorry, that's the wrong one. There we go. So here's our 10-foot ladder, and they have a slightly different setup. They have slightly different variables, but anyways, you can see what's going on when I play the animation. So see the ladder here is falling away from the wall, and the height there, that's what we want to know, how fast the ladder is falling down, meaning how is that h, that distance h, changing with time? Okay, so that's what we're interested in, and we're interested in right when the ladder is 6 feet, when this distance x is 6 feet. Okay. So first thing you do when you do a related rates problem is you write down everything you know and define your variables if you need to. So for us, we have some variables already drawn in the diagram. So we'll just write down what we know. So x, we are told, is 6 feet. We are also given the rate at which x is changing with time, right? In the question it says the ladder sliding away from the wall at a rate of 1 foot per second. That's a derivative. So that's telling us how the distance x is changing with time. So the way I would write that down is dx by dt, the derivative of the function x with respect to time. So how x is changing with time. That's 1 foot per second. So x is a function of time. We don't know what that function is, but when you take the derivative, it's 1. Okay. We are not told what the distance y is. However, we can find it because we know the Pythagorean theorem, right? This is a right triangle. We've got one of the legs. We've got the hypotenuse. And so to find y, we take the square root of 10 squared minus 6 squared. So y would be 8 feet. And the derivative of y with respect to time is what we're interested in. We want to know how y is changing with time. That would tell us how fast the ladder is falling. So I'm just going to circle this, and we want to find this. Okay, so that's the first step when you are doing related rates. You need to write down all the rates you're given, which was dx dt in this case, and all the variable lengths or quantities you're given as well. Okay, so I'm just going to label the steps. So that was step 1. You always do the same 4 steps when you do a related rates problem. Step 2 is you write down an equation that relates your variables. Okay, so we want to write an equation that relates the two variables x and y. We've got a right triangle here, and so one equation that I can think of that relates the two variables together is the Pythagorean theorem, right? So x squared plus y squared is always 10 squared, or 100. That's going to be true no matter where the ladder is or how far it's fallen down. X squared plus y squared is always going to equal 100. Okay, so that's step 2, write an equation. Step 3 is take a derivative with respect to time. Okay, because we want to find dy dt, the derivative of y with respect to time, what we're going to do to this equation is take the derivative of both sides with respect to time, because then dy dt will pop up in there and we can solve for it. Okay, so I'm going to use red to show that. So we want to take the derivative with respect to time of x squared plus y squared, and we want to take the derivative with respect to time of 100. Okay, so here's where you have to do a little bit of thinking. We're taking the derivative with respect to time. Remember, x and y are functions of time, right? They're changing lengths. We don't know their functions, but when we take the derivative, we need to use the chain rule. Okay, so think of x, it is a function of time. You can write it x of t and y of t if you want, if that's helpful. Okay, so we need to use the chain rule when we do these derivatives. So when I take the derivative with respect to time of x of t squared, we would use the chain rule, so we'd bring the 2 down in front, reduce the power by 1, and then multiply by the derivative of the inner function, which is dx dt. And then same thing for the y. So I'd get 2y times dy dt. So you must use the chain rule. Here, that's the key thing. On the right-hand side of the equation, we have a constant, and the derivative of any constant by itself is 0. Okay, so that's step 3. Then we need to solve for, just using algebra, solve for the quantity that we want. We want to find dy dt, so we're going to isolate that. So we're going to move the 2x dx dt term to the other side of the equation. So I'll get 2y dy dt equals negative 2x dx dt. And in order to isolate dy dt, I'm going to divide both sides by 2y. We can save some time when calculating here if we cancel out those 2's, right? There's a 2 in the denominator and in the numerator, so I can cancel those out. Okay, I'm going to go up to the next side here. I'm just going to draw an arrow so you can see where my work is going. So then I'm left with dy dt on one side and x times dx dt all over y. Remember, those 2's got canceled out. Oh, I forgot the negative sign. Okay, and now step 4 is to plug. So the last step is always to plug in known quantities. In this question, we were told x is 6. We calculated that y is 8 and dx dt is 1. And so I can plug those in order to solve for dy dt. So negative 6 times 1 all over 8, and you get negative 0.75. And to get the units, we need to look at what the units of y and t are. So the units of y are feet, and the units of time are seconds, so it's feet per second. The reason it's negative is because it's a rate. So negative rates just mean that quantity is decreasing with time. And that makes sense because the ladder's falling down, so that distance y is decreasing. So the last thing you need to do, since it's a word problem, is interpret your solution, because I need to know that you understand what your answer actually means. So we need to write down a sentence that includes units and the situation. So we can say the ladder, oops. What is that? The ladder is, for some reason, my computer is not liking what I'm writing down, is falling at a rate of 0.75 feet per second. Okay, and the fact that you've said falling indicates that that distance is decreasing, so you don't have to use the negative sign in your sentence as long as you indicate that with your words. Okay, so let me just review that quickly. So first thing you do in a related rates problem is draw a diagram and understand the variables. Okay, in this case, the diagram is drawn for you, but we still need to write down what we know. So we did that. Then you write an equation that relates the variables together. Usually that's either the Pythagorean theorem, or we'll see in the next question is a volume equation. So write down an equation that relates the variables. Then step 3 is take the derivative with each side with respect to time. And that usually involves using the chain rule. And then you solve for the rate that you want in this equation. In this case, that was dy dt. So we used algebra to solve for that. And last step is to plug in your known quantities. Sometimes students want to plug in the known quantities right at the beginning, and that never works because then you end up taking derivatives of constants and you just get 0 equals 0. So you always need to do that last step at the very end. Okay, and then write a sentence explaining your answer. Okay, we're going to try it on another question. So this time we have a cylindrical water tank. This time there's no labels drawn on the diagram here. So this tank is being filled with water at a rate of 2 meters cubed per minute, and we want to know how fast the height of the water is increasing. Okay, so I'm just going to add a little bit to this diagram here. We're interested in this length here, the height of the water as it moves up. Okay, I'll just color it into. Okay, we are told that the radius is 6, and we are also given a rate there. Okay, so let's just write down everything that we know. We know that the radius is 6 meters. Think about this for a second. The rate at which the radius is changing with time. Is the radius changing at all as the water increases or as the water level rises? So think about a cylinder, right? The radius is always consistent no matter how high the water is going to go. So the rate at which the radius is changing is 0. Radius is a constant in this scenario. Height of the water, they don't tell us. So I'm just going to leave that out for now. But they do say that this is what we want to find out. We want to know the rate. We want this. We want to know what the rate at which the height is changing. And they do tell us something about the volume, and you can tell it's talking about volume by the units, right? Meters cubed, cubing a length is always volume, right? So it's being filled at a rate of 2 meters cubed per minute. So we'll use V for volume. dV by dt equals 2 meters cubed per minute. They don't tell us what the volume of the actual cylinder is or the volume of the water. Turns out we're not going to need it, so we'll just leave it for now. Okay, so that's step 1. We wrote down all our variables. We have radius, height, and volume. Step 2, so that's step 1. Step 2 is we need to write an equation that relates volume, height, and radius. So the equation that's going to relate those 3 things is just the volume of a cylinder equation. If you don't know this equation, so for any prism, it's always area of base, so pi r squared times the height. Okay, I will always give you equations like this on a test. I don't expect you to memorize all of the volume equations. Okay, so that's done. Step 3 is take the derivative with respect to time of both sides of that equation because we want to find dH dt. Okay, so that's how that's going to come out. So we're going to take the derivative with respect to time of volume and the derivative with respect to time of pi r squared times h. Okay, so here's where we have to really understand this problem. Some people might look at pi r squared times h and think, oh, that's a product, so I need to use product rule when I'm doing the derivative. But actually, remember that we talked about r. As the water level rises, r is a constant. It's not changing. So pi times r squared is a constant. So when we have a constant multiple, we're free to just take that out of the derivative and just multiply it to the answer, right? So On the left-hand side here, I'll have dv by dt. On the right-hand side, I'll have pi times r squared, right? We take it out. And then I just need the derivative of h with respect to t. Okay, and we can only do that because r is a constant. If r was changing, we'll do another example later where the radius does change as we fill up a tank, and then we cannot do that. We'd have to use the product rule. Okay, and now we solve for what we want. We solve for this. So I'm going to divide both sides by pi r squared. So we get dh dt equals dv dt over pi r squared. And last step is plug in all the known values. And so we know that the change in volume with respect to time is 2 meters. Pi is just a constant, pi. And r squared would be 6 squared. This is going to give us a decimal number, and we'll have to round it off. The question doesn't tell us what we should round to or how many decimal places. So I'm just going to pick 3 decimal places. Hold on, I'm just trying to find the actual answer because I don't want to use my calculator right now. Okay. So I'll use 2 squiggly lines to say that I've rounded it off. On a test or a quiz, I'm always going to tell you how many decimal places to round off to, so don't worry about that. So 0.018 meters per minute. To get the units, just look at what we're finding. So the units of h is meters, right? That's a length. And then the units of t, time, is minute. And you know that because of the dv dt units. Okay, and then we just need to write a sentence. So the height, or the water level, I guess is probably a better way to say it. The water level is rising at a rate of about 0.018 meters per minute. Okay, and this is a positive rate because that water level is increasing. Okay, so every minute it's going to go up by about 0.018 meters. Okay, and that's it for that one. We're going to do one more question and then pause the video. So I'm only going to go over 3 questions in this video, and then I'll do another one for the last 2. Okay, here the next question, I don't have any diagram drawn for you, so we're going to practice doing that. And I have the 4 main steps written for you every time you do a related rates problem, right? So draw a diagram and write what you know, write an equation, differentiate both sides, and then sub the given information. So if you want, I would highlight that. Those are always the same 4 steps you use every time you do related rates. Okay. This is another classic related rates question. Sometimes it's trains, sometimes it's boats or cars. In this case, it's cars. Okay, so car A is traveling west at 50 miles per hour and car B is traveling north. So they're coming together like this. Okay, both are heading towards an intersection. And then we need to find at what rate the cars are approaching one another. How fast are they getting? What's the rate of change of the distance between the cars? Okay, so to do this, we need to just remember our compass. I always say never eat soggy wieners. Okay, so car A is traveling west. So let's draw a line like that. Here's car A. Okay, on your diagrams, don't need to draw a car or anything, just stick to points and lines. It makes it much more simple. And car B is traveling north. Here's car B. Okay, and here's the intersection when they're going to meet. Okay, of course, they're going to move beyond that, but there we go. And now we want to draw some labels on here. So let's call this distance, just because it's related to car A, I'll call this distance between A and the intersection little a. Okay, and I'll call this distance between B and the intersection little b. You could call them X and Y, but I'll just use A and B. doesn't matter. And we're interested in the rate at which these cars are approaching each other. So we also are interested in the distance between the cars. So because we've used A and B, I'll use C for that distance. Okay, so let's write down everything that we know. So that diagram there is totally acceptable. That's what I'm looking for when I'm looking for a diagram. Okay, so I need to see labels, and then underneath it, everything we know about those variables. So A, right now, A is 0.3 miles from the intersection. So maybe I'll highlight some of the information there. Also, we know that car A is traveling west at a rate of 50 miles per hour. That means it's getting closer to the intersection at a rate of 50 miles per hour. So that distance A is decreasing. So that means that you have to interpret that properly when you write down the rate here. So the rate at which A is changing with time is negative 50 miles per hour because that distance is decreasing. So that's an important point there. Make sure you write down a negative rate. Okay, and then B, in the question it tells us that B is 0.4 miles, I believe. Yeah, B is 0.4 miles, and again, we're going to have another negative rate here because the distance B is decreasing with time. So rates are negative when the variable is decreasing. They're positive when the variable is increasing, okay? 60, negative 60 miles per hour. Okay, and C, that's what we want to find out. So we can actually calculate the distance C at this moment. We've got a right triangle here. We'll draw the little right triangle. So A squared plus B squared is going to equal C squared. So if I want to find C, I just take the square root of 0.3 squared plus 0.4 squared. And so C would be 0.5 miles. And what I want to find out is dC by dt. This is what I would like to know. Okay, because the question asks, at what rate are these cars approaching one another? Okay, next step, so that's step 1. Step 2 is to write an equation that relates the two rates. I'm just seeing how much space it got. I'll do that up here. Or the variables, sorry. The 3 variables are A, B, and C. We've got a right triangle, so that's a good indication we want to write down the Pythagorean theorem. So the equation that relates all 3 variables. Okay, we don't have any constants in our equation. Every single variable there is changing with respect to time. So when I take the derivative with respect to time on both sides, I'm going to need the chain rule. Okay, so d by dt of that side and d by dt of the right-hand side. So remember, A, B, and C are all functions of time. We don't know what those explicit functions are, but when we take the derivative with respect to time, we need to use the chain rule. Okay, so the derivative of A squared would be 2A, so power rule, times dA dt. Derivative of B squared with respect to time is 2B times dB dt. And similarly for C squared, you get 2C dC dt. Okay, and I now need to solve for dC dt. So I'm going to divide both sides by 2c. If you're looking carefully, you can save a bit of time in your calculation if you do some cancellations. So notice that every single term in that fraction there has a 2. So you can save time in your calculator if you just cancel out all the 2's and then you don't have to type them in. Okay. So I'll have A dA dt plus B dB dt, and then all over C. So now it's time for, oh, I guess I missed putting step 3. Step 4, which is where I plug in all my known values. So A is 0.3, dA dt is negative 50, B is 0.4, dB dt is negative 60, and C is 0.5. When you plug all those into your calculator, you get negative 78 miles per hour. Okay, and let's just check, should that answer be negative? So I'm just going to zoom out so we can see the whole question. Okay, remember the cars are getting closer together because they're traveling towards the intersection. So it makes sense that dc dt is negative because the distance c is decreasing. So negative rate means the distance or the variable is decreasing. So that makes sense, and we just need to write a sentence. So the cars are approaching, one another at a rate of 78 miles per hour. You could also say, another way to say this, the distance between the cars is decreasing at a rate. Why does it always come up with numbers there? At a rate of 78 miles per hour. Okay, either is fine. And again, you don't have to use the negative sign in your sentence if you imply that. So for example, in the last sentence I wrote there, distance is decreasing at a rate of 78 miles per hour implies that the rate is negative. Okay, so that's it for the first 3 examples. I'm going to stop this video here. I want you to go and practice a little bit before we try the next 2. The next 2 are a little bit harder and involve similar triangles, so I'm going to make a separate video for those. So when we go through those, you can see them there. So I'm just going to erase this. I'm going to show you what I want you guys to do. I would like you to try 1, 7, 9, and 15 before you move to the next video. And then after that video, I want you to try number 23 and the worksheet practice questions. So do 1, 7, 9, and 15 now. Make sure you understand the concept of related rates before you watch video number 2.